this block reconstruction that happens, it is required for most state machine replication or blockchain protocols. But Espresso is a little different, where we don't execute. Right. Our validators don't execute for you. We are a base layer where we provide confirmations, and we provide ordering of transactions. We provide data availability, so anyone who needs it can construct, can obtain the block. But we don't execute. So if we don't execute, nodes actually don't need to reconstruct. So perhaps we don't need to send this block data to everyone. So I guess it is something that we need to figure out if we need that step, and if we remove that step as well, then perhaps we can have some more savings in a finality time.
Awesome. Well, welcome, Kartik. We're here to talk about Espresso system, and then especially about our consensus protocol, and a lot about all the cool work we've been doing in the last couple of months that our amazing engineers and you've been sort of spearheading, and all the improvements that we have. But before we get started, why don't you introduce yourself? Who are you? What do you work on? What are you passionate about? I know it's cricket, but what are you passionate about beyond cricket?
Sounds great. Beyond cricket. So I'm a faculty at Duke, but I guess starting off, I did my PhD at Maryland. Over there, I was working on applied cryptography on topics related to oblivious computation. Midway through my PhD, I did an internship with Dalia Malki and Itai Abraham, where Dalia Malki is also an advisor at Espresso. And at the time, that is when I got introduced to consensus. So. Since then, I've been working on consensus, and currently for the past 6-7 years, I've been at Duke University, where I'm an associate professor, and for the past 3 years, I've been advising Espresso systems. So generally, what am I passionate about? There are 2 areas of research that I work on. I guess the crux of it is in the blockchain space. It being consensus protocols, trying to scale consensus protocols, and trying to see whether you can get other relevant properties that are required in blockchains in conjunction with different consensus protocols under different models. And I also work on privacy preserving computation, which is an entirely different area in my lens.
But what is there, like, something particular about consensus protocols that intrigued you originally, or about blockchains, or what caught your attention or still captures your attention today?
So what caught my attention back then was, I think this internship that I did in 2016. And at the time, to be honest, I was working on an ORAM, or oblivious computation topic. And I went in there to do an internship with Dalia and Itai. We worked on a project, and for whatever reason, we had good results soon enough. And then we said, okay, what's next? And they were interested in the blockchain space. And they were the ones who introduced me to the space and said, okay, there is this problem called distributed consensus, where a group of parties need to agree on a sequence of values, a sequence of transactions. And at first glance, it seems like an easy problem, but it turns out there are so many nuances, so many models, and so many things that change, because of which this problem has kept on being interesting all this while. Back then, the problem that we were interested in was, there is this new protocol called Bitcoin, at the time, which did a good job of achieving consensus. It achieved the required properties, but it was slow, it had poor throughput, and so on. And we were trying to see, hey, how can we use the traditional consensus protocols in that world and try to improve Bitcoin. That is what got me started. But since then, you work through the landscape of exploring, what are the different models that exist, how can you design these protocols, how can you make them faster, and that is what I've been doing for the past decade.
Right. And it's I guess it's also one of these areas that's both, sort of hot in academia, but it's also very much, hot in industry, and it has very real world consequences and real world implications, and things translate over from one way to the other and back, right?
Yeah, exactly. I think so. Every 3 years, someone comes in and asks me, hey, haven't you achieved everything that you need to achieve in the space of consensus? And then, and you feel like it at some point, and then you realize, the industrial application in terms of how blockchains have evolved and what they need based on their requirements, a new requirement comes in, because of which the entire space again, props up, and there are a new set of questions, a new set of challenges that you need to address, and there's a new wave of research that emerges. So I guess it's kind of interplaying, so whatever you do in academia, you try to apply it in the industry, and everyone does that. And based off of that, you get some feedback as well as new additional properties that you require from applications that feeds back into your research as well. So it's a nice cycle of improvements.
Okay. And I mean, this is also kind of, through this bidirectionality is how we get introduced and how you get introduced to Espresso. So we were implementing our consensus protocol called HotShot, which was based on HotStuff, which was originally developed by Facebook's Diem, and Dalia Malki was an advisor, and she said, I'm working with Kartik on this improvement. Can you tell us a little bit about that, how you started at Espresso, and what exactly is HotStuff, HotShot? Yeah.
Right. So HotShot is the protocol that Espresso uses, and it is the protocol that underlies it. At the time was HotStuff. So HotStuff was developed in 2018, 2019 timeframe by Dalia Malki and Ita Abraham and other researchers at VMware Research, and it was the protocol of choice. In the beginning for the DM project, and the key aspect about HotStuff was while many of the earlier protocols, they required, all-to-all communication. So they had a higher communication complexity. With HotStuff, you could achieve what was called as linear communication complexity per view, where not every party has to speak to every other party. So if you're imagining, 10,000 nodes, each speaking with 10,000 other nodes, the explosion in messages could be very high. Whereas with HotStuff, all of them just had to speak to one leader, and the leader would speak with everyone. So that is the property that HotStuff gave you. But at the same time, instead of requiring 2 rounds of votes, which were required for earlier protocols, HotStuff required 3 rounds of votes. And this was a time frame when I guess you started exploring using HotStuff in sometime late 2022 or early 2023. And that is when, Dalia was chatting with me, and she said, maybe we can improve HotStuff to require 2 rounds of votes in the optimistic case, which is the common case where, leaders are not failing. So, and when the network is good. And that got me excited, and we worked on this improvement to HotStuff called HotStuff 2, which only required 2 rounds of votes. And at that point, you had linearity as well as just 2 rounds of votes. So yeah, I guess that is what got me started, and that is when Dalia also mentioned to me about the Espresso project, and that is where I started working with you guys.
Can you explain, actually, sort of already diving into some technical details, why do I care about the number of votes? Why is 3 votes, 2 votes? Why does this, why does that matter?
Right, I think maybe let us step back a little, right? So what are we doing in the blockchain space? So you're decentralizing some application. So decentralizing essentially means you have a bunch of parties, and each of these parties are maintaining some state. And for them to maintain some state, they need to agree upon this state, and this is the consensus problem. So you have some external parties sending transactions, and these parties are the ones who are agreeing on these transactions. They're running this consensus protocol. Right? So to agree on them, they need to communicate with each other. And to communicate, when you communicate, you have sequences of messages that are sent and received, and the amount of communication there is, or the number of rounds of communication there are, that is what will determine how fast something is added to your chain. So this is the time to finality, or the latency of a block that we speak about today. So in the context of something like Ethereum, this is somewhere between 12 and 18 minutes, which means once you propose a block, it can take somewhere between 12 and 18 minutes for you to know that this block has been finalized.
Right.
And in general, for an end user who's submitting a transaction, you would want this to be as small as possible, because it's the time in between, you send a transaction to knowing that this transaction will not get reverted.
Right. And this is, I think, one of the core missions of Espresso is that, sort of when I'm running a chain, sort of that reports back to Ethereum, or I run a roll-up that reports back to Ethereum. And let's say, I want to do something as simple as depositing to an exchange. Well, the exchange really has to wait until Ethereum, or I want to use a bridge, very similar, either the bridge takes some risk and is sort of more expensive, or it has to wait at the very minimum until the block is posted to Ethereum, which roll-ups batch transactions, so that can take like 15 minutes or something like that. And then until Ethereum is finalized, which takes another 15 minutes or 12 minutes. So you're waiting 30 minutes until you actually your bridge goes through, or until you deposit to an exchange is finalized. And with Espresso, the goal was to really cut that down, right? To minimize that time and make it a lot faster and also cheaper to sort of get a confirmation, much faster. So this is kind of where this current project that we started out from. So we started we'd build our consensus protocol. We'd worked on making it cheap for nodes to run operators. We didn't want to run something where operators had to pay hundreds of thousands of dollars, like in Solana a year, to operate a node. So our nodes, sort of in September 2022, you could run a node that costs $100 a year, and that would, but and it was a very stable, it's a stable consensus protocol that was working very well and could handle kind of the load that was passed through it. But there were some downsides of it, like we were kind of thinking it wasn't fast enough. Right? Can you explain that a bit more? And how did we go from there?
So I guess back then, we were also targeting. So I guess one of the goals for us was to not have these beefy machines.
Right.
But at the same time, we were targeting maybe a slightly different architecture at the time, because we were imagining each of the Ethereum nodes is going to run this machine. Right. So run a validator for us. So it's going to be some 10,000 nodes who are going to run the system, which is also why I guess the architecture we chose or the protocol we chose was required. We thought linearity was going to be important. Mm-hmm. Right? And at the same time, we were thinking of a non-homogeneous world where there could be some machines that are big, some machines that are really small, and we wanted to ensure that your protocol works well, because of which we had optimizations like using a CDN, which is some sort of a centralized entity that would help in improving performance.
Right.
So we had an architecture with the CDN, with I think something that I've not explained called a DA committee that existed, and this linear protocol. Mm-hmm. But from there to now, we already are in a world where, we still had a stable protocol, mm-hmm. and something that works very well, but as of 6 months ago, our consensus latency was still around 10 seconds, right? So 10 seconds, if I compare it with, 12 to 18 minutes that Ethereum requires, it's still great, I guess, for mm-hmm. applications. But at the same time, one question you would want to ask is, is 10 seconds enough? Or, it's asked the other way, is it really fundamental that it requires 10 seconds, right? So, at the same time, we also said, the architecture that we were envisioning earlier versus what we are envisioning now is a little different. Now we are running a world where you have 100 parties, 100 validators based off of stake that are running our protocol. And each of them are running dedicated machines. So we don't have like really small machines, but at the same time, as you mentioned, we do not want to spend hundreds of thousands of dollars per validator. It's still somewhere of the order of 100 to 1,000 perhaps, but not higher.
But it's now also, it's more likely to be, it's a professional company that keeps these machines online versus, Jack in his basement, with his Raspberry Pi, or Cindy, or whoever, right? It's a bit more, and we saw that kind of, happening in the Ethereum space. The validators are getting more professional, and we were like, well, we can have those same validators, and there's really only, like, on the order of 100 of them, that can professionally run sort of these machines, and this is much more what our world looks like.
Exactly, and that is what brought us to the set of changes that we set out to do around 6 months ago, to say, can we move from 10 seconds to something less than a second,
right?
And the process, I guess, for doing this was, we started asking, what is the best way to get about it? Should we come up with a new consensus protocol to do this, or there's some other way? And the only clean way to do it is to benchmark, figure out, where your bottlenecks are. Mm-hmm. And based off the benchmarks, figure out the bottlenecks, try to see why the bottlenecks are the bottlenecks, and that tells you, what you can improve. So benchmark, fix, and iterate. So I guess that is what we have been doing in the past 6 months to improve our consensus latency.
So why a bit more, sort of this iterative, let's benchmark, let's fix approach versus like say let's take the newest hottest consensus protocol of the press that you or others have sort of the latest print paper, white paper, and sort of implement that.
So in general, when you come up with a protocol, you're trying to optimize certain metrics, and those metrics you're trying to optimize under certain assumptions. Okay, and there are so these assumptions, you build models out of them, and under those models you're trying to figure out, you get this best metric. So this kind of the model makes several simplifying assumptions in terms of, if I send for example, if I send a message, it will reach within a given amount of time. It does not consider many of the implementation level details that could be a bottleneck.
Right.
I think so this is where models are not perfect. They give you some information, they give you a way to talk, but they're not perfect. Right? So you're optimizing against those models. So there are two places where you can have delays. One is given a model, what is the best you can do, and that is what we try to optimize when designing protocols. And the second is how well is the implementation matching with the assumptions that the model makes. Right? So all until now, I guess we were working on the stack above, where given a model, we tried to optimize it. You could optimize it further, but perhaps the bottleneck could be in the bottom layer, right? And which is what we thought our hunch was, and that is why we said, okay, let's benchmark and let's see whether the implementation actually matches what we assume.
So then sort of what did we find? Like what was kind of the sequence of, or like what were some of the things that we found once we started going down this road and yeah.
Right. So I guess the first set of bits that we did were simple changes that actually gave us very good speed ups in fact. So simple networking changes. When you're sending a message on TCP.
We're always saying biggest bang for a buck, right? Like this is sort of
exactly. I think we want to reduce the latency as much as possible with as little change as we can do, right? So networking changes like, just use TCP no delay. Whenever you're sending a message, ensure that it reaches soon enough, if it's a small message, for example. Another change that we did is if I'm creating a block, the way it works in HotShot today is you send a block and you collect a bunch of votes. That is one round of votes that you do. And then the next leader sends another block and you do another round of votes. Right? So you require 2 QCs or 2 certificates to reach them. And the second leader, it needs to create this block. But could this block creation happen in parallel with whatever was happening in the previous view? And for that, the leader perhaps needs some information like what the previous block is. Right? So for that, we made simple optimizations like sending the block to the next proposer soon enough, so that the next leader can start creating the block and start preparing it, whatever computation it needs to do, it can start doing it ahead of time so that it's prepared to send the block right after. Right? So you can start building the block as soon as the previous proposal is received by the next leader. And then just these modifications already gave us somewhere around, if I remember it right, it's some 2-second block times. So in HotShot, as I mentioned, you have a block time where there is a proposal and a set of votes. That gives you 1 certificate, and 2 certificates is what enables you to commit something. So block time is time for achieving 1 round of votes, and the latency for committing a block or finalizing a block is 2 rounds of votes.
So 4 seconds.
4 seconds. Right.
And this is the big difference, by the way, in terms of architecture between HotShot and something like Ethereum. Ethereum can have like very long forks, so you need many blocks to in order to get finality, to be sure that this block will not revert. Versus in HotShot, sort of once I have 2 blocks in a row, I know that the one, or especially in HotShot 2, the once I have 2 blocks in a row, I know that the block before is never going to change, right? It's final. It's fossilized.
Right. So the other thing that we also did, subsequently was, so we had this at some point, we had this notion of having a marketplace where you would receive, there would be builders who would create these blocks, who would receive transactions, and the builder was the one who was responsible for producing blocks and sending it to the proposer. And this builder, at the time there were a few builders on the planet, but it could be the case that the proposer and builder are not on the same side.
I think there was even only one, I think.
Is that true? Okay.
Yeah.
So it could so happen that you could have a proposer who is on the other side of the planet with the builder, and having communication between the proposer and the builder to just to obtain a block. Right? So that in itself increased latency.
Right.
So, as a first step, what we did is, made sure that there's a builder in every region so that this communication still happens, but the latency is small. Right? As well as as I mentioned earlier, we had this the CDN that we were using, envisioning a non-homogeneous world. But if you have 100 parties where there are dedicated professional validators who are running, you perhaps don't need that CDN anymore.
Right.
So we moved it to a clique network where every party can communicate with every other party.
Right.
And just by doing these changes, we moved from a 4-second latency or 2-second block time to 2-second latency or approximately 1-second block time.
Right. And it's, I guess, like this change, sort of from CDN is like if I have 10,000 nodes, they come online and offline and all of these things, like it's hard to maintain, 10,000 connections at the same time. But if it's 100 nodes, I can actually just maintain. So I need a CDN, I need sort of some other, or peer-to-peer network. We kind of had both, so using the, if I have just 100 nodes, I can, just connect to everybody, and it's easy to maintain 100 connections, even, for cheap nodes or relatively like sort of modest-sized nodes, right?
Exactly. So this is what we've been doing, I guess, until somewhere around November, December, January timeframe. And since then, we've been moving towards, other aspects. Like, I guess, in the earlier architecture, we had this DA committee that I guess we haven't spoken about, but what we had earlier was, we could have 10,000 nodes.
Let me actually sort of, before we go to that, I want to stop at, so we had kind of these first set of low-hanging fruits, which got us, from 10 seconds already down to kind of 2-second latency. But all of those were in our DevNet and our benchmarking, right? So how do we know that, maybe our DevNet, right, it's still, it's still a model, right? It's not entirely the real world. How do we know that this now corresponds, to the real world and sort of, everybody posts benchmarks and you can have the most amazing benchmarks, but do they correspond to reality? Like, what if everything is just on one computer? You can have very good benchmarks. So.
I guess, so what we've done with our DevNet is, so we have a DevNet that kind of mirrors what we have on mainnet with a geo-distributed node setting, and we're trying to mirror as much as possible to what we have on mainnet. Right. So if I'm running some changes,
also sending over the internet, not sending over Amazon's, special pipes. Yeah.
Yes. So if you're running some changes over here, it should directly translate to mainnet.
Right.
And if I understand it right, I guess some set of these changes are already in production now.
Yeah. So we actually we did our big proof of stake upgrade. I think last week or in early March 2026, whenever you're watching this, and sort of like politicians who sneak in an amendment to a bill, we snuck in a massive performance upgrade in there, and I think now on mainnet, our block time is already down to 1.2 seconds. So I think it's a subset of the changes, and so our latency is already down to 2.4 seconds. So we've already seen, sort of a massive improvement on latency just from these low-hanging fruits, and this is what we're going to continue to do. Is this also validates that our approach of having this benchmarking really works in the real world and corresponds to the real world. We're kind of seeing exactly the same performance that we expect from our benchmarking in the real world. So we're very, very confident in our benchmarking, and we're going to continue down this road and push the changes upstream, with a 1 or 2 months delay.
Right.
Exactly. So what are the, we're 2.4 second latency or 2 second latency, but our goal was not, let's make it 2.4 second latency just does not sound as sexy. No, I mean, our goal was to have the latency as fast as possible, and sort of the headline number that we want is sub-second latency.
Right.
So what were, sort of the next steps that we were considering and implementing for that?
So, as I was mentioning earlier, right? I think so. We had this in the 10,000 node architecture, the heterogeneous architecture. We had everyone receiving a share of the data. Mm-hmm. But we also had a specialized committee called as the DA committee. Mm-hmm. There were some 20 nodes which actually received the data, the entire data corresponding to the block.
The entire block, yeah.
And this was directly sent by the leader. Mm-hmm. And this DA committee would first vote on saying that we have received this data, mm-hmm. and a small data availability certificate was created for the fact that this has been received. And every party, before they send the first round of votes for a block, mm-hmm. they verified that this data was available. Mm-hmm. And what we are doing, this creates two bottlenecks. One is you're waiting for an additional round of votes before you do your first round of consensus votes. Mm-hmm. So this additional round of votes from the data availability committee. And second, the leader becomes a bottleneck in that it is sending a lot of data to every party. Mm-hmm. So, I mean, just to be concrete, if you're sending 1 megabyte block, then the leader is actually sending, this 1 megabyte block to 20 parties, and mm-hmm. it's actually, in fact, sending 20 megabytes of information, mm-hmm. as against, what you could have sent, which is, something that is a function of, a small constant, somewhere around 1 to 3 megabytes if you did not do that. Mm-hmm. So our goal now is our goal has been in the past couple of months to get rid of this DA committee, mm-hmm. and just rely on sending some shares or some chunks of erasure coded data to all of these different validators and letting them reconstruct the blocks themselves. Okay. So in a sense, we would improve latency. And yet at the same time, I guess with this change, every party would be able to reconstruct the block. Okay. So instead of sending all of the data to some parties, we would take a block, erasure code it, which means we will break it down into smaller chunks of information, mm-hmm. in such a way that, a small fraction, let's say 34% of the parties can get together and reconstruct the block. Mm-hmm. Okay, so and send each of these chunks, one of these chunks to different parties, mm-hmm. and every party can reshare their chunk with every other party. That allows everyone to reconstruct the data. Mm-hmm. So the leader is still sending information, but much lower than what it did earlier. So earlier it would have been, 1 megabyte becomes 20 megabytes, but over here 1 megabyte would become 3 megabytes, and the factor 3 comes in from erasure coding. Mm-hmm. And every party is also resending, which is the additional amount of work that you need to do, and reconstruction, which is the additional amount of work that we need to do, which we are in the process of benchmarking right now. But this resending, remember, is, if you're sending 3 megabytes of information to 100 parties, that's about 30 kilobytes of information that every party sends to everyone else.
Right. And so it's kind of amazing that, sort of at the end, sort of before, only 20 nodes had the full block, and they could serve this to the rest of the world. Now, actually, every node will have the full block. So every node, in fact, receives more data. It receives the full block data. But through this beautiful, first splitting the block and then, kind of using, I guess you can kind of imagine it like, you have, instead of having one, sort of one bottleneck, one highway, or one, that's sort of completely overloaded, sort of everybody living in a big city sort of knows that one highway that's, completely stuck up. It's, we have 100 roads, going out, and then, sort of going in again, and all of them are sort of have only a little bit of traffic and are much less, congested.
Yes. I guess it's just about parallelizing. So I guess the amount of data being sent is perhaps still the same, or in fact higher, but the amount of work per party is much lower.
Right. Yeah. No, that's a very beautiful, sort of kind of analogy. But yeah. How far?
I guess so. Coming back, I guess so. Removing this DA committee would give you saving, but at the same time, observe what's happening over here. If I'm sending these shares to every party, mm-hmm. instead of sending the vote only to the leader, I might as well vote and send the vote to every other party now. Mm-hmm. So we can go away from the linearity that was necessary or that we deemed necessary for the larger world, the larger the heterogeneous world. Whereas now we can vote with everyone and get rid of the linearity as well.
Right.
And that also, it unlocks something else, which is, running a second round of vote. Earlier, we had propose vote, propose vote. It required 4 rounds of communication.
Right.
But now, because everyone has the first round of votes at the end of round 2, you can do the second round of votes, right then, so that within 3 rounds, you actually achieve consensus. So that is something that we are in the process of implementing. We haven't done it as yet, but there were other things. I think we removed DA committee, we got rid of linearity, but what we also did is, I think after distributing the builder everywhere, we said, okay, we don't actually need the builder anymore. So we got rid of builder and builder communication as well. And with that, already we are in DevNet, we are looking at somewhere that is less than a second at this point.
And I guess we don't really need sort of the builder because in Espresso, unlike in Ethereum, sort of our clients or the users of the Espresso networks are other chains. And they've already built a block, and they're just submitting that block directly they can just submit that block directly to every node. There does not need to be sort of a separate process or a competitive building process, because you kind of know already who's going to build the block, right? It's the chain operators, and each chain has some separate protocol for that. It's not really internal to the Espresso protocol.
Right.
So how much sort of we've done all of these changes we've implemented some of them, like removing the DA, removing the builder, sort of using kind of all-to-all communication. So how much did that get us? Like sort of what are the latest benchmarks?
So I guess what we see on DevNet is somewhere that's less than a second for latency and less than 500 milliseconds for a view time.
For a block
time.
Yeah.
Yes.
That's amazing. So we've achieved the goal sort of sub-second latency.
Yes, but I guess I'm not sure if we are done, are we?
So is this, this is exactly the next question. Is this it, or do we think there's more sort of to gain? How fast can we go?
I guess, just streamlining the second round of votes will get us some saving. Right?
So you think it will get us sort of from 4 to 3, so 25%, or is it somewhere on that order?
Somewhere of that order, right.
Okay.
The other aspect that I think I question is, I think there's something that we should discuss a little more, but this block reconstruction that happens, it is required for most state machine replication or blockchain protocols, but Espresso is a little different, where we don't execute.
Right.
Our validators don't execute for you. We are a base layer where we provide confirmations. And we provide ordering of transactions. We provide data availability, so anyone who needs it can construct, can obtain the block. But we don't execute. So if we don't execute, nodes actually don't need to reconstruct. So perhaps we don't need to send this block data to everyone. So I guess it is something that we need to figure out if we need that step, and if we remove that step as well, then perhaps we can have some more savings in our finality time.
Right. And how much do you have an idea of
It's hard to gauge because we are not removing a round of communication. What we would be saving is the amount of data sent in the second round, in the first round of votes. And I guess there is some compute time that we would be saving as well.
Right.
So it's going to be. It's hard to put a number, but somewhere I would imagine some 50 to 100 milliseconds is what I would expect.
Right.
But I guess the other aspect, right, is what we have is a 3-round protocol. And when you're tolerating 33% Byzantine faults, it is kind of known that we have a lower bound from a paper from 5 years ago, which says 3 rounds are necessary under partial synchrony.
It's the best you can hope for.
It's the best you can hope for if you're tolerating 33% Byzantine faults. But in practice, what could happen and what does happen is that the number of faulty parties are far fewer than 33% for the most part. For 99% of the time that we observe in practice, it is the case that all of the parties are voting, all of the parties are behaving correctly. And the question always is, can we utilize the fact that there are so many more honest parties that exist, and obtain confirmations faster. So
I guess this is a general paradigm in I feel like especially your research, but the general consensus research is that you want to prevent the worst case, but optimize for the best case, because if you do a good job at preventing the worst case, if you sort of disincentivize anyone from actually attacking the network, and this might be, then you will be in the good case, and you also set your incentives right, you use proof of stake, right, all of these things, then you will actually find yourself in the good case, in the most nodes are honest case, like almost always, like 99% of the time.
Right.
So it's, yeah.
And at that point, I think in the good case, you want to figure out how fast you can go, right, or what is the best you can do. And so we have this protocol called Hydrangea that we worked on with Nibesh Shrestha and Aniket Kate last year, where we showed that you can actually achieve consensus in 2 rounds in a world where there are fewer Byzantine parties optimistically. So, as a simple example, one way to think about it is that in the second round of votes, imagine all of the parties vote and you obtain a certificate with all 100% votes.
Right.
At that point, it turns out that you can actually guarantee that no matter what happens subsequently, you're guaranteed that this block will be finalized. Right? So you can generalize this where you can say, you don't require 100% votes, you require fewer votes. And at the same time, if you have some leeway in reducing the Byzantine fault tolerance from 33% to something lower, and you can obtain a combination of Byzantine faults and crash faults, at that point, you can have, again, I think what you mentioned, right? In the bad case, we are still tolerating a large number of faults, Byzantine and crash faults. And in the good case, you would actually achieve finality within 2 rounds of communication. So you would move from 3 to 2.
So it does actually kind of 2 things. It also distinguishes between nodes that are, so we say normally, so it does actually 2 things. So we, not just, sort of the optimistic case, one road, but it also distinguishes a bit better between so-called Byzantine nodes and crashing nodes, right? So we normally we say, I think the classic consensus idea, the way that I was taught it, is like anybody that doesn't follow the protocol is Byzantine. But there's still a big difference between nodes who actively try to attack the network or nodes that are just down. Right?
Yes, I guess, I would say the classic case, if you go back, I guess the more classic case is the crash fault setting. That is used in the industry quite a lot.
Right.
But over there, you're not thinking of Byzantine actors.
Right.
And I guess in the blockchain setting, I guess the more relevant faults, because you're dealing with parties that you do not trust.
Right.
As against in a Google data center where all parties are trusted, the data center nodes are trusted.
Right.
So over here, you're tolerating Byzantine faults.
Right.
But despite being in a world where you don't trust all of these different parties, it is still, so what is still observed in practice, the more common case is not someone who is trying to actively attack a transaction or a block. But what is observed is, some party crashes or loses a network connection and things like that, where, crashes become more relevant.
Right.
So I think in that sense, yes, you're right. You're tolerating both of these. And the advantage of tolerating crash faults as well is because it gives you a higher overall fault tolerance.
Right. Or looking at them differently, like treating them slightly differently, right? And,
exactly.
Okay. So you think this can, now we've gone from 4 to 3 to maybe even 2 rounds of communication. So
exactly.
Maybe we can get, another twice as fast, or
sure.
We'll see.
We'll see. I guess, there are aspects to consider, right?
Of course.
So when you say 3 rounds to 2 rounds, I guess this is where models and metrics may not entirely be accurate, because you are in a geo-distributed setting. Right. So when you're talking about achieving it in 2 rounds, but you require, more votes, because instead of a 67% certificate, you're maybe looking at an 85% certificate.
Right.
At that point, you're requiring more parties to send you these votes. So it's a little more than what we see as 2 rounds right now, and it depends on the geographic distribution of where they are.
Right. And it's really this game of optimizing and where this iterative approach helps. It's really sort of also a bit of a game of whack-a-mole. Where at some point you've optimized everything else, and then you're like, oh wait, this code path sticks out and is kind of slower than we think it should be. and then you dig deep and optimize that, and then you squeeze out more, right? And yeah.
Exactly. I guess so. Once you remove the given bottleneck, so when there are multiple bottlenecks in parallel, I guess you're optimizing for the largest one, and what was not a bottleneck earlier becomes your bottleneck.
Exactly.
So you keep doing this whack-a-mole as you say.
Yeah. No, it's very fun, and I think the goal is, sort of we've been moving, sort of pun intended, extremely fast on this, and the goal is to keep moving fast and make Espresso faster, and sort of deliver the fastest consensus protocol possible. But thank you very much, Kartik. And
thanks, Benedikt.
Thank you.
Thank you.